At first light, Devil's Tower does not look like a hill. It looks manufactured. A single mass of stone rises out of the Wyoming plain with a flat crown, straight fluted walls, and a skirt of broken columns scattered around its base, like the remains of something shattered from above. In winter, the snow settles into the cracks and makes the vertical lines sharper. In summer, the pines below reduce the scale just enough to become misleading. From a distance, it can seem almost understandable. Up close, it becomes worse. The proportions resist instinct. The object is too singular for the landscape around it, too clean in outline, too abrupt in transition from forest floor to sheer stone. It resembles a trunk more than a mountain, a severed base more than a peak, and once that comparison enters the frame, it does not leave easily. What exactly are we looking at? The accepted explanation arrives quickly. Devil's Tower is described as an igneous intrusion, a body of magma that cooled below the surface and was later exposed as the softer surrounding rock eroded away. The long vertical grooves are columnar joints, fractures formed as hot rock cooled and contracted. Other flat-topped landforms are explained through the same broad grammar of geology: deposition, uplift, fracture, erosion, caprock resistance, time. Mesas are remnants of larger plateaus. Buttes are what remain after mesas continue to erode. Volcanic necks, laccoliths, plugs, monoliths, erosional remnants. The vocabulary is dense, established, and at first glance sufficient. It explains why some landforms stand apart. It explains why hard rock survives longer than soft rock. It explains why cliffs form. And it explains why isolated pillars remain after the larger body around them is stripped away. That is the official explanation. It is not incoherent. It is simply incomplete in a way that becomes difficult to ignore once certain physical similarities begin to accumulate. Because description is not the same as understanding. To say a landform is an erosional remnant is often to say only that it survived. It does not fully explain why certain formations so often resemble cut biological forms at scales that seem absurd, or why some of them preserve patterns that look less like random fracture and more like organized growth. The contradiction begins there. Devil's Tower is not merely vertical, it is vertically bundled. Some mesas are not merely flat, they appear sliced. Some isolated rock masses do not taper like hills, but stand with the blunt geometry of truncation. Around many of them there is debris that looks less like ordinary collapse than like splintering. The terrain below can resemble root flare or radial spread. And in the wider record there are other unsettling details. Fossil forests of extraordinary age, mineralized wood treated as stone, coal seams interpreted as compressed plant matter, giant horsetails and lycopsids from earlier worlds, buried organic layers on scales modern ecosystems do not prepare us to imagine. The official explanation can catalogue these things separately. The difficulty is what happens when they are placed beside one another. The hidden theory, stated carefully, is not that every hill is a tree stump or that geology is fiction, or that one dramatic secret was deliberately concealed from the public. It is narrower, and for that reason more serious. It proposes that a small but significant class of landforms now treated as purely geological may in fact be the mineralized bases of an earlier biosphere whose scale has been systematically underestimated. Not metaphorically tree-like, literally tree-derived. Not alive in the recent past, but transformed through burial, heat, mineral replacement, tectonic disturbance, and extreme time until the biological origin became almost unreadable beneath the language of rock mechanics. Under this view, what we call buttes, towers, and certain flat-top monoliths may not be only remnants of volcanic or sedimentary process. And they may be the petrified lower sections of organisms so large that the modern eye refuses the comparison before the investigation even begins. It sounds strange because the scale is strange. But scale is where this theory begins. Start with form. A stump has certain signatures: vertical grain, a broad base, a relatively level top, radial breakup around the perimeter, and a visual disproportion between height and diameter that makes sense only as the surviving lower part of something once much taller. Devil's Tower is not a perfect match, but it is close enough towards the comparison. Its columns run downward like fibrous structure. Its summit is abruptly truncated. The broken stone at its base is not rounded scree from a distant mountain chain. It is angular, fresh-looking, columnar debris, as though the outer wall has been shedding long splinters for centuries. Other landforms repeat parts of this profile. Certain buttes in the American West rise from softer strata with a hard crown and nearly vertical sides, not as gentle accumulations but as standalone forms. Some display circumferential cracking and protective caps that resemble a denser outer rind over a different internal texture. Geology has names for all of this, and some of those names are persuasive, but the eye notices before the glossary does. There is structure here that feels organized. The stone remembers. Then there are the surfaces. When a landform is treated as natural in the broadest sense, any flat upper plane is usually explained as a resistant layer left behind after erosion. That is often true. But there are cases where the top does not read like a tabletop carved by weather. It reads like a cut. The distinction matters. Weathered surfaces usually carry the irregular logic of exposure, channels, asymmetry, slope toward runoff, fragmented ledges. A cut surface, even after long damage, preserves a more abrupt termination. In stump theory, the flat summit is not incidental, it is the central clue. What remains is the lower section after the upper mass is gone. Look at enough isolated towers and mesas and an unsettling pattern appears. Many are not pointed, not domed, not cresting remnants of uplift, but blunt terminations. Their profiles look interrupted. Their sides descend with the kind of parallelism that seems less like random survival and more like consistent internal architecture. This does not prove biology. It does. However, force a harder question. Why do so many natural remnants resemble severed forms more than gradually worn ones? The official explanation answers with time. The alternative asks whether time has been mistaken for transformation. Scale is the first objection, and it is the strongest one. Trees of that size sound impossible. But impossible according to what baseline? Modern forests? Recorded human botany? The geologic past already contains organisms that violate ordinary intuition. Carboniferous forests were not modern forests. Ancient lycopsids and horsetails reached dimensions no living relatives approach. Fossil forests in places like Yellowstone and the petrified forest preserved trunks, root systems, and buried ecosystems turned to stone by mineral-rich water and repeated burial. Coal itself is widely interpreted as compressed ancient plant matter accumulated on astonishing scales. Petrification is not speculative. Mineral replacement is not fringe. Organic structure can become rock while retaining enough pattern for recognition. The question, then, is not whether wood can become stone. It can. The question is whether some bodies currently interpreted as purely geological are so altered, so enlarged by process, and so old that their biological origin has passed outside the limits of accepted comparison. Once that door opens even slightly, the dismissal becomes less secure. What changed was the explanation. There is another category of evidence, and it is less visual than structural. Geological accounts often describe how a feature solidified, fractured, or resisted erosion. But those accounts can sometimes read as process layered on top of form rather than form derived from process. Columnar jointing is a good example. It is real. It is well documented. Cooling rock does crack into polygonal columns. The mainstream explanation deserves to be acknowledged plainly here, because without it the discussion becomes lazy. Devil's Tower's vertical columns fit known patterns of igneous contraction. Similar structures occur in basalt and other volcanic settings around the world. Erosion then exposes those columns and exaggerates the dramatic profile. That explanation is not invented to conceal anything. It is based on repeatable physical behavior. But what it fails to explain fully is why some formations carrying those columns also present such strong stump-like morphology at every larger scale. It explains the grooves. It does not entirely explain the object. It explains the cracking. It does not settle the profile. A column can be volcanic. A bundled columnar mass with a flattened crown, base flare, and splinter field may still deserve a second category of scrutiny. The pattern does not disappear simply because one element of it has a recognized mechanism. Maps deepen the problem. An isolated curiosity can be ignored. A repeated geometry across different basins becomes harder to file away. Across the western United States and in other dry regions globally, there are recurring forms: standalone towers, flat-top remnants, radiating slopes, concentric terraces, abrupt boundary lines between hard central masses and softer outer rings. Geologists read these as the outcomes of differential erosion acting on layered strata, as intrusive bodies or uplifted blocks. Again, that framework often works, but at larger scale the landscape can begin to look less like random survival and more like repeated truncation. Some regions appear populated by what look like fields of reduced stumps, each left at a different height, as though an earlier surface once held much taller structures, now erased above a common horizon. The farther the pattern extends, the less persuasive it becomes to say resemblance is merely accidental. Similarity alone proves nothing. Distributed similarity is another matter. When the same silhouette repeats over hundreds of miles, the question is no longer whether one landform looks strange. The question is why the landscape keeps returning to the same impossible shape. Old photographs and early descriptions contribute something more subtle. Hence, 19th century surveyors, settlers, and military expeditions often described unfamiliar landforms through analogy, because analogy was the only language available. They wrote of chimneys, towers, castles, pipes, tree-like stone, petrified wood, trunks, columns, stems. Those are not scientific conclusions, but they do show first impressions, unfiltered by later classification. Before a feature is entered into a formal category, it is seen, and what people saw again and again were forms that felt built, cut, or grown rather than simply piled. Even in the documented petrified forests, there is a habit of describing mineralized wood as though it belongs to a separate world once it crosses a threshold of age or scale. A small petrified log remains recognizably wood. A massive mineralized body enters geology. A time that transition is understandable. It is also risky. The larger the specimen, the more likely it is to be reclassified according to what it resembles now rather than what it may once have been. The record is still there, but the filing system changes. A thing can move from botany to paleontology, from paleontology to geology, and disappear inside the categories designed to study it. The landscape around these formations matters as much as the formations themselves. If a giant biological structure once stood in place and later mineralized, the surrounding ground would not necessarily preserve clean roots or soft organic transitions. Time would erase almost everything, but it might leave patterns of radial drainage, unusual ring topography, differential compaction zones, and debris fields unlike ordinary slope failure. In many cases, the land immediately around isolated towers and buttes appears disturbed in ways that can be read as root-like buttressing or peripheral breakup. Broad aprons of fractured material spread outward. Drainage lines curve around resistant centers. Outer ridges sometimes form partial halos. Standard geomorphology interprets these as tireless production, runoff adjustment, and resistant unit weathering. That is fair. Yet the alternative interpretation persists, because the same evidence can also be read biologically after mineralization: splintering, buttress decay, compression around a central mass. This is where the debate becomes less about a single feature and more about the limits of interpretation itself. Are we seeing what the process demands or the process our categories permit? There is a difference. A pattern emerges when the theory is taken beyond one American monument. Around the world there are tepuis in South America, isolated inselbergs in Africa and Australia, tower-like remnants in arid plateaus, and steep monoliths whose forms seem detached from the logic of the ground around them. No serious investigator would claim they are all one thing. The world is not that neat. But the repetition of certain traits across continents invites comparison. Flat tops, vertical sides, hard outer shells, resistant central masses, abrupt isolation from softer surrounding terrain. In conventional geology, these are convergent outcomes, different histories producing similar forms, because erosion obeys similar rules. That may be correct, but convergent outcome is also the kind of explanation that can become too elastic, and a phrase broad enough to absorb any anomaly without testing. Whether some anomalies belong in another class entirely. The pattern repeats. Each example on its own can be explained. The collection is more unsettling. A theory begins not when one feature looks wrong, but when many features look wrong in the same way. At this point, it becomes necessary to ask why such a possibility, if there is anything to it at all, would remain unexamined. The answer does not require secret societies or theatrical cover-ups. It requires institutions doing exactly what institutions usually do. Disciplines protect their boundaries. Funding follows accepted questions. A geologist is trained to identify lithology, stratigraphy, fracture, uplift, erosion. A paleobotanist studies preserved plant structures at scales the discipline already recognizes. A mining survey classifies material by extractive value. Land management agencies catalogue stone as stone, fossil wood as protected resource, timber as timber, minerals as minerals. Once a feature enters one bureaucratic stream, it rarely crosses back into another. Classification becomes self-sealing, not because anyone planned it that way, but because systems are built to reduce ambiguity, not expand it. If a mountain is logged as a volcanic intrusion, careers, maps, textbooks, and legal descriptions accumulate around that answer. To challenge it is not merely to offer a new interpretation, it is to reopen the paperwork of reality. Most institutions do not do that unless forced. Economics reinforces the same inertia. Landscapes are managed for roads, mineral rights, hazard assessment, tourism, conservation, and extraction. Those functions require stable labels. They do not reward ontological doubt. A basaltic tower, a sedimentary butte, a petrified log bed, each category carries different implications for ownership, research, and value. The moment a landform stops being just geology and becomes a possible biological remnant of a radically different Earth history, it collides with entire chains of assumption about resource formation, sedimentary timelines, burial events, and ecosystem scale. That does not mean the radical theory is therefore true. It means the cost of testing it seriously is unusually high. Many strange ideas survive only because they are wrong. Some survive because examining them properly would require cooperation among fields that rarely share methods, vocabulary, or incentives. In that sense, the truth can remain hidden without anyone hiding it. It can disappear into specialization, into professional caution, into the simple fact that no one is rewarded for asking the wrong kind of question at the wrong scale. And scale is the recurring wound in this story. Modern people are comfortable with vast time, but not with vast biology. We can accept mountains rising and eroding over millions of years because geology has taught us to think slowly. What we resist is the idea that life itself may once have operated on dimensions far outside modern analogy, not because the rock forbids it, but because the imagination does. A giant stump sounds childish. A volcanic neck sounds adult. One term closes inquiry by making the object ridiculous. The other closes inquiry by making it ordinary. Yet some landforms remain stubbornly unordinary no matter what label is applied. They dominate the horizon with the exact visual grammar of severed growth. They preserve bundled structure, truncated crowns, radial damage, and repetition across regions. The longer one studies the photographs, the maps, the fracture patterns, the mineral records, the fossil precedents, and the bureaucratic classifications, the less the theory feels like a wild invention, and the more it feels like an unanswered filter placed over the landscape. Not a conclusion, a filter, a way of seeing what official language may have trained us not to see. That does not mean every apparent stump is one. It does not mean field geology should be discarded for internet pattern matching. And it does mean some formations deserve a level of cross-disciplinary scrutiny they have not received. High-resolution structural comparison between petrified wood and columnar jointing. Chemical testing for biological templates within anomalous monoliths. Better study of radial landform organisation around isolated towers. Re-examination of old survey notes, mining records and early photographs without the certainty of modern labels. These are not impossible tasks, they are simply unfashionable ones. What matters is that the question can be formulated in a way that is testable. If a landform is only an igneous intrusion, the evidence should confirm that cleanly. If it preserves signatures of replacement along an earlier biological architecture, that should also leave traces. The issue is not whether every strange claim deserves belief. The issue is whether every strange pattern deserves dismissal. So the argument compresses into something simpler and more unsettling. Perhaps these formations are exactly what we are told they are. Rock masses shaped by heat, fracture, uplift and erosion over extraordinary spans of time. Perhaps the resemblance to Stumps is a coincidence produced by physics and our hunger for pattern. But perhaps a small number of them are records of a world whose living scale has been reduced, mineralized and mislabeled until only the silhouette remains. A base without a trunk without a canopy, a landscape full of severed memory. The stone remembers, the record is still there. What changed was the explanation. And the real question is not whether the theory sounds strange, but whether anyone with the tools to verify it has seriously looked.